As risen upon new era of QEEG-based neurometric approach in neuropsychiatric disorders in 1977, QEEG has been loved by many researchers and mental care specialists and applied for ADHD, autism, depression, traumatic brain injury, and neurodegenerative disease for a long time. However, in considering its potential clinical value, usage of QEEG hasn't been expanded into mainstream medical practice yet. It takes lots of time and effort for clinical practitioners to learn the skill for visual inspection and manual processing of raw EEG signals and understand and clinically interpret various QEEG findings. To overcome this limitation, iMediSync has adopted the advanced signal processing algorithms and AI machine learning method on our EEG analyzing cloud platform, iThinkBrain. Advanced Mixture ICA or AMICA and deep learning algorithm for automatic detection of noise component will make you get a reliable cleansing result of noise EEG signals. You can experience not just in EEG frequency power or power ratio at scalp level, but also in the approximated source power and brain functional connectivity map with 3D visualization by just one click. We also developing AI algorithm using video clip features to present the complex and dynamic components of EEG. Research solution of iThinkBrain supports clinicians to make group comparison very easily, monitor the change of EEG after treatment, and get a quick insight about specific EEG characteristics of certain disease groups, especially when you could access our EEG norm library. EEG signals change dynamically during developmental and aging period. That's the reason why age-dependent normative database is important. However, sex hormone could strongly affect the cognitive function and behavior, and there are differences in instances of neuropsychiatric disorders such as ADHD and dementia. According to this, we have developed sex-differentiated EEG normative database and found rather different trajectory of age-dependent EEG changes according to the biological gender, especially during adolescence and elderly, while we apply the more advanced machine learning fitting method. You are expected to get more differentiated and significant comparison result using iThinkBrain's normative database.
Among many blind source separation algorithms, iThinkBrain adopts adaptive mixture independent component analysis called AMICA with the best performance in terms of mutual information reduction. EEG measured at scalp level composed of various cortical oscillation, hence separation and reviewal of independent component provide us a novel window for EEG comprehension. EEG measured at the scalp level usually separate into actual neural signals, EOG, ECG, EMG, and etc. All components can be categorized into neural component or noise component based on their time dynamics, frequency spectra, and spatial location. iThinkBrain provides a standardized AI pipeline employing convolutional neural network to determine the noise component such as EOG, ECG, EMG, and etc. Such pipeline tremendously reduce the time needed for noise removal. iSync Brain's noise removal algorithm adopts independent component analysis, returning a cleaned EEG data. It especially works well for EEG recording contaminated by EOG, EMG, or ECG during entire recording, which could not be analyzed using traditional methods. Each independent component equivalent dipole location are provided through the dipole fitting model. iSync Brain displays each noise component determined by the noise removal algorithm on the upper left corner. In this example, slow wave component localized at F8 electrode was determined as a noise component. Slow wave component arising from unstable contact with the scalp and fast wave component due to surface muscle tension usually shows an overly localized topomap pattern. On the other hand, cortex-originated neural component generally show a wider distribution, reflecting a field effect. iSync Brain shows MNI source location for all neural components. From the example, we can observe that the source is located at BA Brodmann area 19 parahippocampal gyrus. We can presume that a fast alpha component has been generated from the parahippocampal gyrus, reflecting the symptoms of a PTSD patient.
iSync Brain norm comparison displays absolute and relative powers computed at sensor level, z-score color-coded relative to the norm. You could check the map in 1 Hz bins or specific frequency bands. 19 channels absolute or relative spectra at sensor level can be displayed in linear or log scale with the abnormal regions highlighted. There are multiple methodologies for conversion of scalp level EEG into source level oscillations through solving of an inverse problem. iSync Brain employs S-Loretta, which is well known for its great localization performance. S-Loretta calculates 16,008 voxel level z-score distribution. This is then displayed through a 3D interactive viewer. iSync Brain adopts 68 ROIs from Desiccant Killing Atlas and returns a list of most deviant ROIs in terms of the z-score. Through the 3D interactive viewer, 3D z-score maps for various regions, including the medial side, can be visualized, or in any arbitrary directions. Moreover, it provides connectivities among 68 ROIs calculated from the imaginary coherences. They are displayed as z-score color-coded lines relative to the norm. iSync Brain also provides a live z-score API service for specific age and sex, a real-time neurofeedback training through comparison with the QEEG norm database. Heart rate variability is another clinically applicable electrophysiological data representing variability in the RR interval from the ECG signal. Spectrum analysis on HRV reveals activities of autonomic nervous system, which includes sympathetic or parasympathetic nervous system. One of our iSync platforms, iSync Heart, provides an HRV norm comparison service. As you can observe from the graph, HRV dynamics show a decreasing trend with age. Relatively lower HRV value at a given age reflect poor resilience of the autonomic function. iSync Heart automatically detects R peak from the measured ECG signal and extracts RR interval after noise corrections. Henceforth, both sympathetic and parasympathetic activities are calculated through norm comparison. iSync Brain has another set of functionalities specialized for research purposes named iSync Brain R. iSync Brain R provides an over-group statistical comparison for two or more independent groups. The example shows an ANOVA group comparison returning significant differences in the frontocental and occipital area. iSync Brain also provides comparisons between the groups pre-post interventions. The example shows comparison between an active intervention and a placebo intervention groups, showing significant differences at the parietocentral area. iSync Brain R also provides a healthy control group data of matched age and sex from the iSync Brain's normative library. Allowing the researchers to collect such healthy control group data from the web dramatically accelerates development of disease-specific biomarkers or discovery of EEG phenotypes. iSync Brain M is a QEEG biomarker for early screening of AMCI, currently proceeding for KFDA approval. iSync Brain M calculates and displays the probability of the subject having AMCI through age-based comparison with the normative age dynamics of brainwaves.
Unlike conventional neural imaging data such as MRI, PET, etc., each data contains the time dynamics with high resolution. iSync Brain M constructs a video clip from the collection of instantaneous EEG snapshot and QEEG features reflecting the time dynamics. The figure shows configuration of the conventional CNN learning model which employs 2D images. iSync Brain M stacks 2D snapshots along the timeline, creating a 3D video clip data. The 3D video clip data undergoes a deep neural network with its structure shown in the figure. Snapshots comprising the video clips are extracted using iSync Brain signal analysis functions, which yield the spectrum, the time frequency, topo map, source, connectivity, and phase data.
We will continuously update iSync Brain's platform with state-of-the-art computational neuroscience and AI machine learning technology, and contribute better clinical services in neuropsychiatric and neuromodulation area. Thank you.